What if the insurmountable barrier was never truly insurmountable, but merely a silent lie we told ourselves? For generations, the cosmos whispered of a future just beyond our grasp. Its vastness presented demands too great, its inherent costs too prohibitive. This perception defined our reach, our potential, for so long. But now, in the relentless pursuit of Mars settlement, something fundamental is shifting. The very fabric of that silent lie is being shattered. Consider the Raptor 4 engine. It stands poised to redefine our understanding of cosmic feasibility, not through a sudden, fleeting wonder, but through sustained, relentless engineering. This is a stark evolutionary leap, specifically designed to make lunar and Martian settlements economically viable. For decades, we looked back at the F1 engine, a marvel of 70-year-old engineering, producing 680 metric tons of thrust at a mere 7 megapascals. Raptor 3, its direct predecessor, already generated approximately 280 metric tons at 35 megapascals, achieving a remarkable thrust-to-weight ratio of 171:1, with a mass of 1,525 kg. The Raptor 4 pushes further, targeting beyond 300 tons, potentially reaching 330 tons of thrust. This isn't just an incremental increase. It's a fundamental reimagining of raw power married to efficiency. Its projected cost-effectiveness targets a figure closer to $100,000 per ton of thrust, over 10 times more efficient than the Merlin engine's estimated $1 million per ton, and significantly below Raptor 3's $250,000 to $500,000 range. Raptor 4 will enable a full Starship stack with over 11,000 tons of liftoff thrust, more than thrice Saturn V's output. Future Starship variants, deploying 42 Raptor 4 engines across the booster and ship, are expected to carry over 200 tons to orbit, a substantial increase in payload capacity. The sheer scale suggested by these numbers alone hints at a paradigm shift in our access to space. Yet, raw power, while grand in its ambition, is only half of the equation for establishing a permanent presence beyond Earth. The other half, perhaps the more insidious challenge, lies in how we return, how we survive the brutal crucible of re-entry into our own atmosphere. Starship Flight 12 revealed a monumental step forward in this unseen struggle. It successfully demonstrated a remarkably intact heat shield after enduring a truly brutal atmospheric re-entry. Retired astronaut Chris Hadfield confirmed this observation as a critical advancement, one essential for potential reusability and, by extension, affordable space access. The conditions faced were not accidental. SpaceX intentionally chose a high-energy suborbital trajectory for this test, forcing a steeper, more aggressive entry angle at approximately 7.4+ kilometers per second. This decision created a harsher heating environment than a shallow orbital decay would have presented. The heat shield endured peak temperatures near 1,450 degrees Celsius, 2,600 degrees Fahrenheit, demonstrating its robustness precisely within the tile's upper operating range. The fact it held spoke volumes. This triumph, however, was not born overnight from a single stroke of genius. It was forged from the relentless, often punishing, lessons of prior challenges. Flights 10 and 11, aggressive tests of the V2 heat shield, meticulously revealed deep-seated issues that demanded resolution. Plasma intrusion from tile gaps presented a formidable problem, alongside the oxidation of experimental metallic tiles. These trials, while appearing as setbacks, were, in fact, crucial data points. They directly led to critical adjustments in design and material science. Metallic tiles were definitively abandoned in favor of enhanced ceramic systems. A significantly improved crunch wrap insulating layer was developed by Flight 11, which also successfully tested exposed ablative backup material in high heating sections. Flight 12's V3 architecture directly incorporated every insight gained. It featured redesigned tile geometry, explicitly intended to better distribute mechanical loads, drastically improving tile retention and significantly reducing plasma intrusion. All of this was supported by stronger attachment hardware, itself developed from rigorous V2 post-flight analysis. Each scar from previous trials became a precise blueprint for resilience, etched into the very design. What we are witnessing, then, is not merely an isolated engineering feat, however impressive. It is the systematic forging of an industrial highway across the void. an infrastructure where only dreams once dared to tread. The relentless power of Raptor 4, coupled with the demonstrably resilient shield of Starship, is not just propelling us into the infinite. It is fundamentally redefining humanity's place within it. If this is truly the dawn of sustained cosmic industry, a reality built piece by painstaking piece, what other silent lies have we been telling ourselves about the universe, and, more profoundly, about our own boundless capabilities? The question lingers,